At this point in Chapter 11, we've learned a couple of counting principles. The first one was called the fundamental counting principle, where we multiply the number of choices for each decision to count the total number of outcomes. In the last section, we looked at counting permutations. Permutations were different from the fundamental counting principle in that with permutations, we're looking at selecting more than one item per category. And we learned that for a permutation, the order is important. That means if I rearrange the items, I get something new. In section 11.3, we'll learn about combinations. Combinations are yet another way of counting arrangements. It's another counting principle. These are related to but distinct from permutations. With a combination, we're still looking at selecting more than one item per category, and it's not replaced. Now, this time, the order of selection is not important. If the order of selection is not important, then the outcomes are called combinations. So make sure you make that distinction. With permutation, the order matters. That is, if I rearrange the items, I get something new. Like if I rearrange the letters in a word, I get a new word. For a combination, the order does not matter. An example of a combination then would be your pizza. If I want to get 3 toppings on a pizza, it doesn't matter the order in which those toppings are placed. If I rearrange the toppings, I still have the same pizza. So let's look at how combinations are different from permutations. In example 2, we're going to list all possible 3-letter combinations of the set math. If you'll remember in section 11.2, we listed 24 3-letter permutations of the set math. But here we're listing combinations. So one possible combination is the word MAT. Now, in a combination, we're assuming that the order doesn't make a difference. So if I rearrange these letters, I'm not going to get anything new. So any arrangement containing the letters M, A, and T are equivalent to this one MAT. So we're not going to count the items where we've rearranged the letters. So another possible combination here would be M, A, and H. And again, if I rearrange those letters, I'm not going to get anything new. And how about A, T, H? And there's one other possibility, M, T, and H. So those are all the combinations of the set M, A, T, H. The only other arrangements I could get would be a rearrangement of the letters that we already have right there. So combinations are very different from permutations. Now, just like we had with permutations, we can count combinations without having to list all of the individual items. Here's the formula. The number of combinations of n total items taken r at a time is given by NCR, remember we had a P there before, equal to n factorial divided by r factorial times n minus r factorial. Now, if you get rid of that r factorial, you've got the formula for a permutation. But a combination is going to have this additional factor in the denominator, which makes the total number of outcomes less than permutations, right? If you have a bigger denominator, your fraction is less. So there's always going to be less combinations than permutations. Now, let's practice applying this formula to the example we just went through. Use the formula to calculate the number of combinations from example 2. In example 2, we had a total of 4 letters, and we were finding 3-letter combinations. So I'm going to use the letter C here in place of the P. So in the numerator, we have 4 factorial. In the denominator, we have r factorial, that's 3. And in parentheses, 4 minus 3, and then factorial. So let's go ahead and follow the order of operations. That is, I'm going to evaluate what's inside parentheses first. 4 minus 3 is 1, and then we can evaluate that factorial. So we end up with, in the numerator, 4 times 3 times 2 times 1. In the denominator, 3 times 2 times 1, and then 1 factorial, of course, is just 1. Now, when we cancel like factors, everything but the 4 cancels. And the result is 4 divided by 1, or just 4. And remember, up here, that's exactly what we listed, 4 total combinations. Remember, we had 24 permutations when the rearrangement of the letters made something new. But as far as combinations go, we're not looking at rearranging the letters. There's only 4 combinations. Now, as you probably already suspect, your calculator does a great job with combinations, just like permutations, and we're going to find it in the same location. The first thing I'm going to do is enter the 4 on my home screen. I'm going to go to the Math Probability menu, and we can observe option number 3 is in CR, combinations. So at this point, we have permutation, combination, and factorial that we use from this Math Probability menu. Make sure you choose the right one. We want combinations. We're going to do 3 at a time, and of course the outcome is 4. So you can very efficiently evaluate permutations and combinations with your calculator. So let's try several examples, and the evaluation, as you'll see, is very simple with a calculator. What I want you to really think about as we go through this information is, how do I distinguish this from a permutation? Remember, in a permutation, the order matters. In a combination, the order does not matter. It's pretty simple in this section because we're focused on combinations, but when all this information is jumbled together on an exam where you have to decide between the two, make sure that you know the difference. So example 4 says, in how many ways can a 4-person committee be formed from a club of 30 members? Remember our club of 30 members where we selected president, vice president, secretary, and treasurer? Well, in that case, the order mattered, so we used a permutation. But here, from the club of 30 members, if I'm just forming a 4-person committee, think about it. If I pick 4 people out of those 30 and I sit them at a desk, and then I tell them to rearrange their chairs, switch seats with someone at the table, I haven't formed a new committee, right? So the order of selection is not important. Therefore, we use a combination. So we've got a total of 30. We're going to choose them 4 at a time. We can evaluate this with our calculator. 30, we're going to go to our Math Probability menu, choose option number 3, 30C4, and we get 27,405. 27,405. Remember, that's a lot less than the slates of president, vice president, secretary, and treasurer. So there's always going to be fewer combinations than permutations. Now, don't you think these formulas are a little easier than the formulas we saw in the finance chapter? Absolutely. This is a pretty straightforward and easy chapter. I hope you're enjoying it. Example 5. How many different 5-card poker hands are possible if dealt from a standard deck of 52 cards? So we have a total of 52 cards, and we're selecting them R at a time. So in order to choose between permutation and combination, I have to determine, does the order make a difference? So imagine those 5 cards in your hand, and let's suppose you rearrange your cards. Okay, so you're going to change the order of the 5 cards that you have in your hands. Do you have a different poker hand? The answer is no. So if I rearrange the items, I don't get anything new. Therefore, we count with a combination, not a permutation. So let's type this into our calculator. 52 Math Probability, we choose combination C. 52C5 gives us 2,598,960 different poker hands. 2,598,960. 2,598,960 possible hands that you can be dealt from a deck of 52. That's what makes the game interesting, all the different possibilities. How about example 6? How many lottery tickets are possible if a player must choose 5 numbers from 54? So 54 is our N, 5 is how many we're choosing at a time. And in this particular lottery, if you rearrange the numbers, you still have the winning numbers, right? In playing the lottery, you just have to select the winning numbers. There are some special games where you do have to get a digit in the correct position, but as far as general lotteries go, if you have the winning numbers in any order, then you have won the lottery. So that means we're counting this with a combination. So let's evaluate with our calculator. 54 C5. So we have 3,162,510 possible arrangements. 3, 1, 6, 2, 5, 10. 3,162,510 possible arrangements. Now, here's a sneak peek of the probability section coming up soon. Again, we haven't defined probability officially, but you can use your intuition to figure this out. What is the probability or likelihood that you win this lottery, right? We've counted the total number of possible ways that we can choose 5 numbers from 54, but we know only one set is the winning set of numbers, right? So 1 out of 3,162,510 possibilities. So if we turn this into a decimal, we get a very small number. Notice the scientific notation there. I'm just going to approximate this, 3.16. I'll just round it off. 3.16 times 10 to the negative 7th. 3.16 times 10 to the negative 7th. The squiggly equals again just means I have approximated it. Now, let's move the decimal from its current location 7 places to the left. A negative exponent says move left, positive move right. So we have 1, 2, 3, 4, 5, 6, 7. That's the decimal value. Let's turn this into a percent. Remember to go from decimal to percent. We're going to move the decimal 2 places to the right. So it looks like we're going to have 4 leading zeros and then 316%. Make sure you put your percent sign. So if this is the tenths place, this is the hundredths, this is the thousandths, this is the 10,000ths. That means it's less than 1/10,000th of a percent that I choose the winning number, right? Do you think that it is likely or unlikely? Yeah, we're going to learn how to classify that as an unlikely event in the next section. Okay, let's look at a couple more examples. A student club has 20 members and is made up of 4 freshmen, 2 sophomores, 5 juniors, and 9 seniors. How many 4-person committees can be formed? Okay, so we're looking at committees, which means the order doesn't matter. If you rearrange the people in the committee, it's still the same committee. So we know we're going to be dealing with combinations, but we're going to look at a special composition of the committee. Example A, what if we have to have 1 person from each class? Well, in this case, we can use the fundamental counting principle. We can say, how many possible freshmen do we have to choose from? How about sophomores, juniors, and seniors, right? So we had 4 freshmen to choose from, 2 sophomores, 5 juniors, and 9 seniors. So we're simply going to use our fundamental counting principle to multiply the number of choices for each decision, right? Number of available students for each spot. And we would get, in this case, 360 possible committees. Still quite a few. What if we have to have 2 freshmen and 2 seniors? Now, notice how this is different from example A. In example A, I was choosing 1 person from each group, but in example B, we're looking at more than 1 person from a particular group. The order still doesn't matter, but this time we're going to use a combination as opposed to a permutation. So let's look at the freshmen. We've got a total of 4 freshmen, and we're going to select 2 at a time. right? And as far as the seniors go, we had a total of 9 seniors, and we're going to select 2 at a time. Now, I've got 2 decisions here, right? How many ways can I choose my freshmen? How many ways can I choose my seniors? The fundamental counting principle tells me to multiply the number of choices for each decision. So I need to multiply these outcomes. Now, I'm going to calculate these one at a time so I can see the details. Let's calculate 4C2. That's going to give us, there's 6 possible ways to choose 2 freshmen from 4. And then I'm going to calculate 9C2. This is going to give us the total number of ways we can choose 2 seniors from 9. So 6 here and 36 here. So let's go ahead and multiply those together, and we get a total of 216 possible committees. Now, to finish, what if we don't have to have a special composition? What if we can have any mixture of classes? Then in that case, we're going to say we have a total of 20 members, and we're going to pick them 4 at a time, disregarding class. So 20, math, probability number 3, 20C4, and we end up with 4,845 different committees. So make sure you read carefully and look at the subtle differences, read the descriptions, think about fundamental counting principle, think about order. If it makes a difference, we go with permutation. If it does not, we go with combination. Now we're going to finish with a fun little example here, an example from our local area. A local Amarillo restaurant used combinations to calculate the number of ways to build their burgers. So think about going to a restaurant like this when you can choose different types of breads, different types of meats, different vegetables. And if you want to put vegetables on your hamburgers, maybe you want only pickles, or maybe you want 3 or 4 different things. Maybe you want pickles, onions, and tomatoes, right? So there's a lot of different ways that you can form your particular burger. So check out this menu. They have the calculation here, and it says over 1 billion ways to build them your way. Now look at those C's. What do you notice there? They are counting combinations. Now, you might get a little picky if they don't stack up your burger right, but if I put pickles, onions, and tomatoes in any order on your burger, then if I rearrange that order, it's still the same order, right? Still the same burger. So they're using combinations, and their result came up with something over 1 billion different ways to build their burgers. So you are an educated individual of our community. You can read local menus and you can understand the math. Hope you find that kind of interesting.